Okay, hello. We're going to be talking about fluid pressure and force. Okay, so the basic idea of this is that when you are computing the pressure of a fluid, the idea is that the deeper you go, the more there would be water pressure. So you've probably experienced this if you have swam underwater, and as you dive down deep, you can feel the pressure building as you go deeper, and so that's true. And so we know that force is equal to pressure times area. Okay, and we can find the fluid. So the pressure, so the concept is that the pressure will increase the deeper you go. So in fact, we have that the pressure at a depth h of y in a fluid of mass density rho is given by pressure equals rho times g, which is the force of gravity, times h of y. So this is rho is the mass density of the fluid. So that's going to depend on what kind of fluid it is. Is it water, or is it something more viscous than water? Okay, so that mass density of the fluid. This is the force of gravity. And then this h of y is telling me the depth. Okay, so that is how I would compute the fluid pressure. Okay. All right, and then we know that the force is going to be the pressure, which I've found a way to find the pressure, times the area. But again, what we said is that that pressure is going to change for different depths. So if we think about some sort of a lot of times we'll be talking about some kind of a plate, of some sort of a plate. Maybe I drew this as a trapezoid looking thing here. And so at different water levels, at different depths, we're going to have different amount of pressure. So what we're going to do is we're going to take a little slice of this thing here. And what I'm going to do is I'm going to compute the amount of force that fluid is exerting on that slice of the plate. And then I will add up all of the slices at all the different depths that I have. So what I need here is this to be some width, and that width might change as the depth changes. As I can see here with my trapezoidal thing, as I get deeper, it looks like my plate is widening. So I'll have to come up with some sort of a function that gives me the width as a function of my depth. And then this depth here, I'm going to call h of y. This is the depth. This is the width. Okay, and then the thickness of my plate here is my delta y. So the area of my slice is going to be equal to w of y times delta y, or dy. Okay, and then, okay, and so then the pressure on this slice, or the force on my slice, is going to be equal to, well, it's going to be the pressure, so rho times g times h of y times w of y times delta y. And so that would be the amount of force on that little tiny slice. And so if my delta y is small enough, then I can kind of assume that it has the same pressure for that whole little thin slice. And so if I want to say the total force on my plate, it's going to be an integral of this rho g h of y. Again, this is the pressure times w of y dy. And again, this is the area of my little slice, and I'm going to be adding up all those slices from my minimum depth, which I'm going to call A, to my maximum depth, which I'm going to call B. Okay, and so that's going to be the way I would set up that kind of an integral. Okay, so let's talk a little bit about the rho and the g and the units that we might use. So let's talk a little bit about units. Okay, so if I am dealing with metric units, then my mass density of water is equal to, so this is my rho, which is my mass density of water, is going to be equal to 1,000 kilograms per meter cubed. And then my g, which is the force of gravity, is 9.8 meters per second squared, which you probably know that, or meters per second. No, it should be meters per second squared because it's yeah, okay. And then the force measure is going to be measured in newtons. And so newtons are kilograms times meters per second squared. And so you can see how that's all going to work out when you compute all those things. Okay, so if I'm using standard units, so that's all metric, and if I'm doing standard units, then you have this weight density of water. So the rho and g are going to be combined. So the weight density of water will be this rho g together, which is going to be 65 pounds per cubic feet. And then the force is going to be measured in pounds. Okay, and so you may run into some problems that are using standard units and some problems that might be using metric units, so you need to be able to know the difference between the two. Okay, let's do an example on the next page and then we'll be finished. Okay, so here is an example. All right, so we're going to do this one where we have let R be the plate in the shape of the region y equals sine x for 0 less than or equal to x less than or equal to pi over 2. So it's going to be like this. So the shape of sine x. So the plate is going to look kind of like that. So this is going to be my R. And then I can say let the water level be at y equals 1. So that means my water level is here at y equals 1. there's the top of my water. And so then I want to set up the integral. For fluid force. Okay, so my integral, so if I think about a slice of this guy here, what will the depth of that be? What will be my h of y? Well, my y coordinate of this point here on my graph is going to be that part of my graph. So that will be y. And so this portion here, which would be the depth, is going to be 1, which would go all the way down to the x-axis, minus y. So h of y is going to be equal to 1 minus y. So that would be the depth of my slice. So what I'm going to be writing here is rho g times h of y times w of y dy. And I'm going to integrate that from my shallowest depth, which is 0, to my deepest depth, which is 1. Okay, and so I have the integral from 0 to 1 of rho g, and then the depth is going to be 1 minus y. And then the width is going to be the width of that slice. And so if I think about that, that is at the point x comma sine x, or I could think about that point as being the point, sine inverse of y comma y. So in other words, I could think about the x coordinate of that being sine inverse. So then the width, so the sine inverse would be this amount here. So the width would be pi over 2 minus sine inverse of y. And then I've got my width written there as a function of y, because I'm going to be integrating with respect to y. And so this width times that thickness of the dy is the thickness of my slice. This is my area. And then this rho g times the depth is my pressure. So if I multiply pressure times area, that gives me the fluid force. So that would be the setup for that integral.